The University of Texas at Tyler Houston Engineering Center is located on Hayes Road on the west side of Houston, Texas. It consists of several floors leased from Houston Community College and teaches mechanical, electrical, and civil engineering programs. It is here in these hallways that the seeds of greatness were planted. Seeds that would become Team Body Language. Who is Team Body Language? The pride of the Houston Engineering Center, Team Body Language consists of Andrew, Abraham, Victoria, and Benjamin. 4 electrical engineering students, all with an interest in space technology and exploration. It is this interest that led them to the Texas Space Grant Consortium, or TSGC. The TSGC selects student teams from around the state to participate in NASA-led research projects, to work towards presenting their findings in a competitive showcase at the end of each semester. Our team, Team Body Language, was lucky enough to be selected to work on a project entitled Tactile Display for Spacewalks. What is a tactile display, and how can it be used for spacewalks? When the International Space Station needs external repair, astronauts must venture outside to conduct a spacewalk. Astronaut Doug Wheels Wheelock called spacewalks a visual and emotional feast for the senses. The view of the Earth from orbit was so overwhelmingly beautiful. He found it difficult to focus on the delicate work of repairing a mass of metal hurtling at 5 miles a second through the vacuum of space. In fact, Wheels suggested they should instead be called a space ballet of fingertips, because the act of maneuvering about the station using only your fingertips while processing a limited visual field, monitoring audio communications chatter, and interpreting warning signals is so demanding. Human senses have a limited bandwidth. If this bandwidth is exceeded, the sensation will be ignored, undistinguished from the other incoming signals. While on spacewalks, astronauts rely on audio communications to maintain awareness of their suit conditions, receive instructions or updates from mission control, process incoming warnings, and orient themselves with the spacecraft. Processing all this information through one channel is possible, but potentially tiring and overly demanding for long spacewalks. To reduce the burden on a single sensory channel, an unoccupied sensory channel can be used to share the load. This is where a tactile display can be useful. Under the advice of our NASA mentor Rico Aceves, we decided to demonstrate a proof of concept for the benefits of a tactile display in high-stress, high-information flow environments. Mr. Aceves suggested we design a tactile display for mission control to help manage the flow of input information that operators must process. The average mission control operator is monitoring multiple screens, multiple audio communications channels through their headsets, and also listening for audible warning signals that could alert the controller to check a certain portion of their visual display. Designing for mission control is also simpler, cheaper, and will iterate faster than designing additions to spacesuits. We 3D printed a behind-ear device to hold the vibrating motor to the operator's neck. Now let's talk to our team member Ben to see a little bit about how the device works.
The behind-the-ear device, like any other audio headset, is put on behind your ear. There's a vibrating component which will ultimately be held against your neck in our finished prototype. So I'm just going to hold it right here like this. The system is built to detect 3 different audio pulses: a short 50 millisecond pulse, a slightly longer 100 millisecond pulse, and 5 repeated 100 millisecond pulses, and it responds to each one in a different way, as you'll be able to see here. For the short pulse, 1 beep. For the longer pulse, 2 beeps. And for the repeated pulse, 3 beeps. And that's how it works.
Hearing the alarms becomes less peripheral and more personal. We believe this is especially appropriate for alarm detection, but there are several further applications, both in spacewalks and here on the ground, that we intend to explore. We'll test time-varying patterns like waves or rotations to indicate to the user to move or turn around. At the very least, multiple nodes permit a more colorful tactile language, which we believe is our most appropriate next step, and where our current efforts are focused. Through further refining our signal detection and adding more tactile locations to our display, we'll be able to process more diverse signals, convey more meaningful tactile patterns, and convey as much information as possible.